So welcome everybody to the last virtual seminar for this autumn season of the Qatar Centre for Global Banking and Finance. We are very lucky to have Christian Matthes here today with us, who will talk to us about the extreme weather and the macroeconomy. Christian Matthes is at Indiana University, and before that, he was also at the Richmond Fed, so has both a central banking and an academic, background. And Christian, I am really looking forward to hear about this paper, so I'm going to leave the floor to you without further ado. Please. Sorry, let me just remind the participants that they should feel free to ask questions. They can either raise their hands or put their questions in the Q&A box that they find below, and I can also relay, and therefore thus relay the questions to you. Thanks. The floor is yours.
Thank you so much, Francesca, for the kind introduction and for having me. Unfortunately, only virtually, but it's still great to give this presentation. So this is a paper I've been working on with two co-authors for a while. Namely my former colleague at the Richmond Fed, Tuan Phan, and Hee-Soo Kim, who is a fantastic grad student here at Indiana. So look out for her when she'll be on the market in a couple of years. As the title suggests, we're interested in the interplay between weather and the macroeconomy. Oops, let me try to swipe my slides here. Sorry. As always, I have a technology problem at the beginning. Let me try to undo this problem. Now it works. Perfect. So in particular, what are we interested in? We're interested in whether or not extreme weather matters for the US economy. There has been a lot of previous work thinking about the effect that weather can have on various economic outcomes. However, the previous literature has focused on one of two things. Either, if it has taken a macro perspective, it has focused on developing countries mainly and lower frequencies for data availability reasons. Okay, think about annual data, maybe even think about 5-year periods, things like that. Here I mentioned a couple of papers. First and foremost, probably is a very well-known paper in AJ Macro by Dell, Jones, and Olken. Very famous panel study on the effects of temperature in particular on economic growth. There have been others, Solomon Hissang and Gina, on the effects of cyclones, Beckinson and Barrage. Those are, again, low frequency and thinking about the developed economy. For the United States, people have looked at this, but they've looked at more micro level evidence. Okay, think about a hurricane hitting Florida. What happens in that area of Florida? Okay, is output depressed there for a long time, or does it come back? These are all very, very important questions, but they're not macro questions. For the when people have tried to answer this question for the United States, they focus on a micro perspective. Again, very useful, but here, as macroeconomists, we're going to unapologetically take a macro perspective. Not only are we going to take a macro perspective, but in contrast to this previous literature that has looked at more economic growth at an aggregate level, we're going to look at business cycle frequencies. Now, a key question you're probably going to ask yourself is, how can you answer these questions at a business cycle frequency? What's the identification? And that's going to be a big part of this talk, trying to convince you that we have a credible identification scheme. And related to that, why have people not done this before? There's a measurement problem. How do you measure the effects of extreme weather? Well, you might say, well, that's easy. There certainly are estimates of damages from hurricanes. Fine, that's what people have used before. That's true. But there's many different ways in which extreme weather can affect the economy. It's not only hurricanes, it can be droughts, can be high temperatures or low temperatures. Measuring damages there is much harder. So instead of trying to assess extreme weather via its economic damages, we're going to use direct measures of extreme weather. Okay, now how are we going to do that? Well, here's kind of one thing that's well known. The US, like most of the world, is basically covered in stations that measure weather, that tell us within this little small grid of the United States, little part of the US, how much precipitation was there, how was the temperature, things like that. Okay, fine. But again, I said, extreme weather is multidimensional. We're going to have to aggregate this. Thankfully, we're not the first ones to face this problem. We're the first ones to maybe use this to think about this in a macro context. But who really thinks hard about weather damages? Actuaries. Okay, so it actually turns out that the Society of US Actuaries has actually created an index of extreme weather events for the United States. And that's what we're going to use, and that's going to help us to identify extreme weather events and shocks to extreme weather. Okay, because we're going to really play by a macro perspective, and we're going to try to identify extreme weather shocks. So a big part of this talk will be introducing this data set and trying to convince you that it's actually sensible. It's going to be a broad data set just by construction, because we want to have a broad measure of extreme weather events. Later on in the talk, I'm going to drill down deeper into specific elements of this. But first, I want to introduce this very broad measure of extreme weather events. Okay. Once we have this measure, what are we going to do? We're going to ask not only what are the effects of extreme weather on the economy, but have these effects changed over time? Why is that interesting? Well, one, we're obviously all aware of climate change, so these events could become worse. On the other hand, maybe adaptation has become better. Maybe technological advances have more than offset the increased effects to climate change. Okay, so it's really not clear which way this will go. And what we're going to do more specifically in this paper, we're going to use a nonlinear time series model. Why nonlinear? Because we're looking at effect, we want to assess how effects have changed over time. And we're going to find, just a little preview, we're going to find that the effects of these shocks, but not their volatility, have become more severe. Okay, it's going to be interesting. I think we think a very interesting finding. Okay. Now, as I said, the very first part, a key part of this paper, what's really new is that we're using this data from this Actuaries Climate Index. It's literally called I'm going to call it the ACI, the Actuaries Climate Index. What is this? It's a monthly index, so that's already good, right? Because I told you before, we want to look at business cycle frequencies. And it's an index of climate risk based on 6 different measures of climate risk. All these 6 measures share some common aspects in their construction. Namely, the sample starts in the 1960s. These actuaries, they're going to use the period from 1960 to 1990, and they're going to call that their benchmark period. Okay, and they're going to see how these different measures fluctuate through the benchmark period. And then they're going to assess how these different measures have changed after the benchmark period. Okay, what are these different measures? First, a measure of extremely high temperatures. Basically, they're going to look at distribution across the United States of temperatures. They're going to look at the 90th percentile of the distribution, and they're going to ask how often is the temperature above the 90th percentile for the benchmark period. Obviously, within the benchmark period, it has to be 10%. That's the very definition of a percentile. But after the benchmark period, it's not clear anymore. Similarly, they're going to look at the lowest 10% of the temperature distribution. They're going to ask, how often are temperatures below that? Again, in the benchmark period, it has to be 10%, but not afterwards. Then they're going to look similarly at the frequency of high winds, precipitation, in particular heavy precipitation. That's what they're going to study here. They're going to look at droughts and changes in sea levels. Okay, obviously changes in sea levels are only measured at a much smaller number of points compared to temperatures and precipitation. All right, so I have these 6 distinct measures of extreme weather. Now, how in the world am I going to aggregate them? I'm going to do there. We were again following actuaries. We're going to do something super simple. We're going to first standardize each component relative to the benchmark period. We're going to subtract the mean from the benchmark period and divide by the standard deviation. Okay. Okay. This is the mean and standard deviation in the benchmark period. And then once we have these different measures, we're just going to sum them up and take the average. That's down here. Okay. So take these very different measures, standardize them relative to the benchmark period, take the mean. The only thing that might be of interest here is that there's a minus sign here. Why is there a minus sign? Because these are low temperatures. So we want to, so we're going to add them. So just because they're not talking, because it's basically the flipped version of the 90th percentile, it's going to enter with a negative sign. Okay. Because we kind of really want to measure extreme weather events. Here's what the components look like. Okay. Here, for example, low temperatures, high temperatures, precipitation. For some of them, you see a clear trend even in the benchmark period. For example, here, the sea level. Whereas for others, like high temperatures, the trend only emerges, or at least mostly emerges, only after the benchmark period is over. Okay. So these are the components. What does the overall index look like? Here's what it looks like. Okay. The red and blue bars are the individual entries of the aggregate index over time, starting in the 60s, all the way up to a recent data points. And the black line is a 5-year moving average. Okay. And you can see just by eyeballing it, it fluctuates around 0 up until the end of the benchmark period. And then there's an upward trend afterwards. So this is going to be our measure of extreme weather. We're going to dig in deeper later and assess specific components of the ACI. But first, we're going to take this broad measure. Now, what are we going to do? As I said, we're going to build a multivariate time series model to assess how changes in this ACI, which I'm going to identify in a specific way, map into changes in economic variables. What economic variables are we going to study? We're going to study IP growth. We're going to study CPI inflation, a short-term interest rate. That's the Fed funds rate, except during the zero lower bound period, we're going to use the Wu-Shia shadow rate. So I think it can become negative. And we're going to have the unemployment rate. For some of our questions, we're also going to look at core CPIs separately. So that's over here. A couple of comments I want to make about this data. We're going to seasonally adjust everything, okay? Both economic data and the ACI. But we are going to have robustness checks later where we do no seasonal adjustment at all and our results are robust. Second point I want to highlight is IP growth. We have monthly data. In the US, GDP is not available at monthly frequency, at least not officially. So it's fine, you can use IP growth, but I want to highlight one thing. We're talking about the effects of extreme weather here. One area that we know is going to be hit when extreme weather happens is agriculture. Agriculture is not included in IP growth. So in some sense, the results we're going to show in terms of the real effects of extreme weather are a lower bound because they do not directly include effects on agriculture. Going back to the previous literature that looked at lower frequencies, for example, the work by Dell and co-authors in AJ Macro, they did look at agriculture and they did find obviously very strong effects. Now their work again was mainly focused on developing countries, but we do think, for example, if a drought hits the US Midwest, that's really going to affect agriculture here. But we're not directly going to have that in our data due to the frequency mismatch that we would otherwise have. Okay. And why do we not want to go to a quarterly frequency? We don't want to go to a quarterly frequency because we see that some of these spikes in the ACI are pretty short-lived. So we're worried about temporal aggregation issues if we go to a quarterly frequency. Okay. So next, I'm going to build an econometric model, but let me maybe stop here and ask if there are any questions about the data.
So there aren't from the public yet, but actually I have been wondering a bit about but maybe I'll tell you quickly. But so I was wondering whether the fact of aggregating all the different indices might dampen the effects, and that maybe having them separately would, at least some of them, the more crucial ones, would be relevant.
Yeah, no, that's absolutely that's a great question. That's totally relevant, and we're going to do that. So I'll have that later, because that's really important, because some of the effects I'm going to show you are going to be driven by some components and not others. So I'm going to try to tease that out later. Absolutely.
Okay, wonderful. That's really interesting. I look forward to it. Thank you.
Thanks. So next, let's go to an econometric model. So I have these time series that I showed you. Sorry for going back and forth so often, but I'm going to put these variables in a time series model. Now I'm going to do this in 2 steps. First, I'm going to show you how I want to identify shocks to this ACI, right? So we're going to play the standard macro game of trying to find a mapping between one-step ahead forecast errors in our model and structural shocks, uncorrelated structural shocks, okay? I'm first going to write that down in a linear model, and then I'm going to augment the linear model to allow for nonlinearities. Because as I said, one thing we're interested in is whether or not these effects have changed over time. Okay. So how am I going to do that? So I'm basically just repeating here on the slide deck what I just told you. Okay, so I'm going to define a forecast error. That's the actual outcome. So YT is a vector that includes all these variables that I just showed you in the plot previously. And I'm going to subtract the 1 period ahead expectation of that same variable. Okay, so this is a 1 period ahead forecast error. Where does the economic model come in? Where does the statistical model come in? Well, the statistical model is going to give us the 1 period ahead expectations. Okay. Now, what I want to do then is I want to say my structural shocks, in particular, this weather shock that I'm interested in, this shock to this ACI, that's going to be a linear combination of the forecast errors. Okay. In other words, that's going to be given right here. Now, as usual, the big discussion in macro is how do you identify? Okay, what kind of restrictions are you putting on sigma, which is a matrix that governs the mapping from our structural shocks, these ETs, to the forecast errors, UT, that we are actually observing. So what I'm going to do is I'm just going to assume that ACI, that's the weather index, is ordered first in YT, okay, just because to make the notation precise and what comes next. So here's my identification assumption. I made this look all fancy, but it's really the most basic identification assumption that we teach all our undergraduates when they first see VARs. In fact, what we're going to assume is that all variation in the ACI coming from unexpected changes from 1 month to the next. So all variation in ACI coming from UT is due to the ACI shock. What does that mean? Basically, our ACI shock, which I call here E1T, is just a rescaled version of the forecast error in ACI. The rescaling just happens to make this E1T shock have unit standard deviation. Okay, so this is really what is often called a Koleski type identification assumption. Okay, so I'm putting zeros in the sigma matrix. Now let me be very clear about what this means and what it doesn't mean. This means from 1 month to the next, any fluctuation in extreme weather are not due to economic events. They're not due because the US or the European Union have increased production. Okay. What does that not mean? This does not mean that in the long run, our extreme weather events do not depend on economic outcomes. That is absolutely not true, because the predictable part of ACI can depend on economic outcomes. Okay, it's just the month-to-month unexpected variation in extreme weather is not a function of what happens in that month to the economy. That's all we're assuming here. Okay, and that's what I'm going to run with. Now, so I made this case in a linear model, but now now that we've settled on the identification, and if there are any questions, please just stop me and ask. But now that I've told you about the identification, what I'm going to do next is I'm going to talk more about how we get the forecast error. Okay, what is the statistical model for our vector of observables? Okay, so let's think about what we want. We want a model that is transparent, easy to interpret, where time variation is presumably modeled as something that happens at a relatively low frequency, because we think about these changes, climate change or adaptation, not being sudden changes, okay? And we want something that links closely to a linear model, because that's where I started off my identification discussion with. Okay, so that's kind of my wish list. And here's what I'm going to do. I'm going to use smooth transition VAR. In some sense, smooth is maybe a slight misnomer for some of the specifications that we use, not our benchmark. And here's the idea. The idea is simple. Our model is nonlinear, but in a very simple way. Our vector yt is governed by a convex combination of two linear VARs. First part of the convex combination, second part of the convex combination. Okay? And now, what I'm going to have to tell you, and I'm going to do a lot of robustness checks here, is what are the weights on the convex combination, okay? So we see when C tilde is 0, then the only thing that matters is this part. When C tilde is 1, the only thing that matters is this part. C tilde always has to be between 0 and 1. Okay, so this is a type of VAR that has been used a lot in macroeconomics. Think about Auerbach and Gortnichenko. People at King's College, Michele Piffer, has done really important work on the econometrics of these models. And what we're gonna do a slight little twist on how a lot of other people have used these models. Okay, what we're going to do is we're going to directly feed in our indicator C tilde. And what are we going to do? As a benchmark, we're going to do something super simple. We're just going to do a linear transition. Okay, C tilde starts at 0, ends at 1. What does that mean? It means we're really comparing a convex combination. We're really modeling the VAR. We're really modeling the dynamics of YT as starting out with one VAR and ending up in another VAR. And in between, in the middle of the sample, it's a convex combination between these two. Okay. And we're going to really look at a lot of robustness here, and I'm going to highlight which of our results are robust. Okay, and so this is exactly where the key difference is with a lot of the literature in terms of the econometrics. A lot of the previous literature basically models C tilde as a nonlinear function of some underlying economic variable. We're going to directly feed in the C tilde just to make things very transparent, right? Right now, what we're doing is we want to basically say there's one set of VAR coefficients for the beginning of the sample, one for the end, and then if you're in the middle of the sample, you're taking an average. That's all we're doing. Okay. Now, let me again highlight why time variation is important. We're building on this big literature in microeconometrics and applied micro that has studied weather-related events. And in particular, there's a very famous paper by Michael Greenstone and co-authors where they basically try to tackle from a micro perspective this study of adaptation. And what they're doing is they're basically splitting the sample, okay? Note that splitting the sample is nested in our approach. If instead of using this C tilde function, I use a step function. And that's actually one of the robustness checks I'm going to show you at the end if I have time. Okay. So because we're interested in adaptation, allowing for time variation is really key. And what we want to do this in a very transparent way. I've worked a lot on time varying parameter models, much more complicated than this. But the nice thing about this is it's really very transparent where the time variation comes from. Okay. Now, how do we estimate this? As I said, for example, Michele has done really important work here. We're following. I think we're following a similar approach to what Michele has done. We're doing a Bayesian approach. Now, if you're interested in this, we're approximating the posterior by a sequential Monte Carlo as something that's been around for a while. We cite here kind of the two standard sources, Herbst and Schorfheide in their textbook, or Mark Bognani and Ed Herbst. I should have also obviously cited Michaela's work. Now, here's something that's really important. Okay, I don't want to get bogged down in the nitty-gritty. This is not an econometrics talk, but there's one thing I want to say. Whenever you do a Bayesian approach, people rightfully ask, what is the prior? Here, I'm going to say, okay, I have this on the next bullet point, so I don't want to jump ahead. First, we're going to use standard priors or standard class of priors for the vector autoregression, okay? But the key point, the one thing I want you to remember about the priors is the priors are the same for the beginning and the end of the sample. So any difference in results between end of sample and beginning of the sample that I'm going to show you next is due to the data. It's due to the likelihood function, right? In Bayesian inference, we combine the prior and the likelihood function. Any difference has to come from the likelihood function, i.e., it has to come from the data. Before I go to the results, let me see if there are any questions.
Yes, there actually is one. So let me relay it to you from Laurent Ferrara, who asks if you have looked at the logistic-like transition that are also usually used in the smooth transition VARs. If you have kind of done robustness around that as well, if you have checked that.
No, not logistic, but we have different shapes. I'll show you different shapes later. That's a great question. It's exactly the right question to ask. And I'll show you, we could do logistic, but in fact, I think at some point we didn't do logistic, but we did something like a quadratic, and that the results were very similar. That's not going to be one of the specifications I'm going to show you today, but I'm going to show you some that definitely don't look linear, okay? Yeah. Thank you very much for that question. Now, let's go to the results. So this is the key figure. This is the key figure. I'm going to zoom into different parts of this figure in a second. I just want to first describe the layout. What this shows are the impulse responses to a 1 standard deviation shock to ACI, okay? The bold lines are medians, and the shaded areas are 68% confidence bands. The blue impulse responses are those at the beginning of the sample, red ones at the end of the sample. Okay, so let's zoom in into different parts, different variables, and see how things have changed over time. First, ACI itself. 1 standard deviation shock at the beginning of the sample versus the end of the sample. What do I want to highlight here? Something we found stunning. We didn't expect this. The impact, because it's a 1 standard deviation shock, the impact here is what is the estimate of the standard deviation. It's basically the same at the beginning and the end of the sample. So the shock itself does not become more volatile. It is true that after the end of the benchmark period, the level of ACI goes up a lot, but not the volatility around that level. Okay. So that's the first kind of stylized fact I want you to remember. Now, here's probably the most important response, IP growth. Okay, so at the beginning of the sample, it's up here. 0 is included in the posterior bands. Nothing is happening. End of the sample, we do see a substantial decrease in IP growth. Now, one thing you're probably going to ask is, how big are these magnitudes? I'm going to come to that. I'm going to show you a variance decomposition, okay? Because I want to relay how important these things are. Next, unemployment rate. 0 included in the posterior bands for all horizons. This is up to 40 months at the beginning of the sample. Barely not included at the end of the sample. I want to be very upfront about this. The unemployment response is not robust across specifications. If you put a gun to my chest and ask me, do I believe unemployment goes up at the end of the sample, I would say yes, because most specifications point that way, but some don't. Okay, so let's take that with a grain of salt, because I want to convince you that these other results they are robust. Let's look at inflation. beginning of the sample, CPI inflation actually goes down after a weather event. Whereas end of the sample, CPI inflation goes up, which is kind of interesting if you compare it to the response of IP growth, which you can barely see here. I hope you can see it a little bit. Because we often think about, okay, the joint impulse responses of prices and real activity can be used to distinguish demand and supply shocks. Here it seems if you really think about kind of this nomenclature of demand and supply shocks, it seems that has switched from the end of the sample, from the beginning of the sample to the end of the sample. Okay. Now, there is a response of industrial production. There is a response of CPI inflation. What does the Fed do? Turns out, Fed does nothing. Okay. So as you saw at the very beginning of the talk, one of my co-authors is at the Fed. So we were like wondering, okay, what do we make of this? You want to show that to your bosses. Well, let's dig in a little bit deeper here. Okay. So what I'm going to do is the following. I'm going to re-estimate my model. I'm going to add one additional variable in. I'm going to keep all the variables I had in before. I'm going to add one additional variable, namely core CPI. Okay. I should say, sorry, one thing I should have mentioned before, sorry. All these variables, IP growth and inflation, are year-over-year log differences. Okay. So all these magnitudes are year-over-year. I'm going to highlight here the responses of CPI inflation and core CPI. Okay, again, as before, blue beginning of the sample and red end of the sample, sorry. The responses look very similar to, for the variables that are included in both specifications, responses look very similar. But here's the story. Core CPI doesn't move, neither at the beginning of the sample nor at the end of the sample. So it makes sense that the Fed doesn't really react to this because it's basically all in energy and food. And that makes sense, right? For a lot of these events, suppose there's a drought, well, that might affect food prices. It, might affect electricity prices if there's a hurricane somewhere, But since it doesn't affect core, it makes sense for the Fed not to move. The next thing I want to dig a little bit deeper into is industrial production. Okay, I'm going to run the same VAR as before, but I'm going to replace year-over-year IP growth with log IP. Okay, so instead of having the growth rate, I'm going to use the level. Why do I want to do that? Because I'm interested in whether or not I really want to make very transparent if there is a long-run level effect, or if this is just a one-time growth rate thing. Where the growth rate does the level bounce back, or does it take a long time for the level to recover? And here's what we find: beginning of the sample, no response of the level of IP. At the end of the sample, there is obviously a response. It's consistent with our growth rate estimates, but it's also very long-lived, right? So we could have teased that out from our growth rate VAR, but instead, just to make things simpler, we re-estimated the slightly different specification. And so there's been a lot of discussion in the literature about what are the effects of the weather events. Dell, Jones, and Olkin, for example, discuss this a lot. And we find these persistent effects on the level of production after weather events. And this is reminiscent of other papers in the literature. Here we have Isang and Gina's finding on the effects of cyclones. Obviously, cyclones are a much more narrow category of weather than our broad measure of, that encompasses many categories. But nonetheless, they also find these very persistent effects. Similarly, there's a recent paper by Nelson Mark, Kimberly Burke, and Kurt Chadwick. I hope I got that name right. Where they look at, where they basically redo some of Dell, Jones, and Olkin using a little bit more sophisticated econometrics, and a great paper, also at a lower frequency, and they also find these very long-lived effects. So why is this useful? Well, if you think about equilibrium models that people study to assess the effects of climate change, they often have to calibrate a damage function. Okay, what does climate change do to output? Well, here we provide further evidence that these effects are probably very long-lived. Since I'm talking about equilibrium models here, let me spend 1 minute on making one important distinction that I didn't emphasize enough, or didn't emphasize at all at the beginning. Namely, our results are really about historical data. What has happened in the US up until now, okay? Given all the literature on, for example, possible tipping points in climate dynamics, we don't want people to extrapolate necessarily, at least at long horizons, our results, okay? So usually when you estimate a VAR, you think, okay, I can extrapolate that into the future, and these are my results. Here, we're very well aware. We have captured time variation up until now, but it would be very hard using our model to extrapolate far into the future, because there's just so much uncertainty about issues like tipping points and so on, things that are probably better studied in an equilibrium model. And I think why there is a very fruitful interaction possible. Always in macro, but especially in this literature, between more statistical approaches like ours and approaches based on equilibrium models. Now, a question you've probably tried to ask is, how important are these shocks? You showed me these impulse responses, they're significant, but are they economically meaningful? What am I going to do is the following. I'm going to do a variance decomposition. I'm going to ask, and how am I going to do that? I'm going to say, what's the variance decomposition on impact, basically, and 1 year after. So what's the 1 year ahead forecast error variance decomposition and the forecast error variance decomposition on impact? Kind of a standard approach in macro. I have done this for the beginning of the sample and the end of the sample. Let me focus here on the second subset of results, the end of the sample, and I've kind of magnified that a little bit here. What does this table show you? Okay, so we're looking at all our variables here. I'm going to look at the different horizons. H0 is impact, H12 is a year out. And then I'm going to look at the variance decomposition, 16th percentile, 50th percentile, and 84th percentile, right? Because I'm uncertain about the parameters of the model. There's a posterior distribution of the parameters of the model. So I'm also uncertain about the variance decomposition. So I want to convey this uncertainty. First, ACI, not surprisingly, both on impact and 1 year out, this ACI shock basically explains everything in ACI. What about in IP growth? Well, for the 50th percentile, right here, about a little less than 2%. Okay, I'm going to, in a second here, well, you can already see it at the bullet point at the bottom, but I'm going to try to put this in perspective. But I want to, before I put things in perspective, I also want to say the 84th percentile, not such an extreme percentile, we're already at almost 5%, both on impact and 1 year out. Okay, so there's a good chance that 5% of IP, of fluctuations in industrial production are due to these weather shocks. For the unemployment rate, median is about 1%, but again, 84th percentile, not that unlikely, more than 3%. Similar numbers for CPI inflation. And then for the interest rate, even though the responses were insignificant, there is a good chance that these weather shocks explain about 5% of the fluctuations in the nominal interest rate. Okay? Now, how do we benchmark this, right? When you see these numbers, are those big, are those small? Well, what I like to do, and it's not really an apples to apples comparison, but I'm still going to do it. Forgive me for that. Let's compare to the famous Matthes-Wouters AER paper. That's a big dynamic equilibrium model for the US economy, one that is often used in central banks. Okay. Now, what do these guys find? They're going to also estimate their model with Bayesian methods. They're going to look at the variance decomposition at the posterior mode. So it's not quite comparable to my posterior percentiles, but still, at the posterior mode, a monetary shock explains 10% or less of GDP growth and inflation at similar horizons to the ones that I've used here on impact and 1 year out. Now think about that. Think about how many papers have been written about monetary policy shocks. If those explain about 10% of fluctuations, this shock explains 2%, could explain up to 5% of IP fluctuations, okay? So if there's so many papers written on monetary policy shocks, maybe we should look at these shocks a little more closely as well. And by the way, I'm not saying that as somebody who's critical of the monetary policy literature. I've written a lot of papers using monetary policy shocks. I'm still writing papers analyzing monetary policy shocks. I think it's very important. I just want to kind of put these things in comparison. Are these as important as monetary policy shocks? Maybe not. Not yet, okay? We're talking in the future, they might become even more important, as I talked about in terms of like tipping points and things like that. But even nowadays, at the end of the sample, these can already matter quite a bit for economic fluctuations. So what drives our results? Francesca asked me how individual components of this ACI matter. So that's what I'm going to do next. Here's my plan of attack. I'm going to take my standard VAR, the benchmark VAR I showed you, and I want to add one additional variable at a time, namely one component of ACI at a time. So I'm going to have both aggregate ACI and this individual component in my VAR. I'm going to order the individual component first. So I'm going to look at shocks to that individual component. Okay, that's the game I'm going to play. I'm first going to summarize the result, then I'm going to show you the impulse response. So what about precipitation? Precipitation has no effect on IP growth, but does increase unemployment. Okay. Here we see, first column now is the precipitation component of the ACI. Obviously, it increases the ACI. Doesn't do much for IP growth, as I had on the previous slide, but it does increase unemployment at the end of the sample. Now, why is that? Well, if there's heavy precipitation, maybe there's less hiring going on farms in agriculture, for example. Okay. Interestingly enough, we do actually see a response here of the short-term interest rate at the end of the sample. An increase, though. I'm not sure what to make of that. Second, what's going on with temperatures? Our patterns for IP growth are really driven by changes in both high and low temperatures. Okay, let's look at the high temperature shock first. Okay, an increase in that increases ACI at the beginning of the sample, doesn't do much for IP growth at the end of the sample. Very similar to what we saw in our benchmark results, substantial decrease. Similarly for the low temperature shock. Now, one thing you have to be careful with the low temperature shock, I pointed out at the beginning, it does enter with a negative sign. Okay, so positive shock to this ACI, to this temperature component, lowers ACI. Okay, so we gotta basically flip the impulse responses of everything here relative to what I showed you previously. And then you also see a decrease in IP growth at the end of the sample. What about our patterns for inflation? Those really, one component that matters for inflation are sea level changes, okay? So we see here sea level changes. Beginning of the sample give us a decrease, a shock to sea level changes. At the beginning, give us a decrease in inflation. At the end of the sample, an increase, just like we observed for the aggregate pattern. So we see that there certainly is heterogeneity across these components. That's why it's interesting to look both at the aggregate component first, but also then disentangle these different components. Let me maybe pause here and ask if there are any questions, because what I have next is robustness checks.
I have a question in the meanwhile. So I am very interested in the fact that these different components affect the different variables in a different way. I was waiting to see which one of the components was driving the different effect on inflation, for example, and kind of trying to explain this kind of switch from, demand to supply shocks, or I don't remember which way it was going actually, but from one to the other. And so I wanted to get a sense from you, if to kind of discuss that a little bit more. Tell me a little bit more about which of these components then you have identified as driving that effect, or.
Yeah. So I mean, here's one thing that's hard about this. Okay, so we have not done much more here because there's one caveat. the caveat is that these components are not orthogonal, obviously. Okay, so there's obviously correlation between them. So we're trying to capture that a little bit by including aggregate ACI in these VARs. But if we wanted to do more here, this is just the way I view this component analysis is more suggestive more than anything else, because if I wanted to dig even deeper, I would want to for example identify a shock here to sea level that's orthogonal to everything else, right? Because you could think about unexpected changes in sea level could be driven by increases in precipitation or things like that, or could be correlated with that. So my answer, which is a bit of a cop-out, is at this point I don't have much more to say about that, but it would be very, very interesting to look at it. Yeah, absolutely.
No, I see the issue. Let me relate to you Michele Piffer's question as well, and then I think we also have a question from David. So Michele asks if you have looked into the reverse effect, the causal effect going from economic activity to ACI. He says your forecast area variance decomposition at the 1 year ahead suggests that ACI is completely exogenous to economic activity, but it would be interesting to explore.
Yeah, no, absolutely. So I mean, so I think we thought about it, but we didn't really come up with a really good interpretation, a good identification scheme for that. But it's definitely a really good question. Right now, I mean, if we identify, obviously, as you said, if we identify the ACI shock the way we do, and we added kind of a real activity shock, well, I would be pretty sure that not much would change, because the ACI shock that we identify that basically drives everything in ACI, as Michele also pointed out. But it would be a really interesting extension.
I think David has a question.
Hi, Christian. Fascinating presentation. Just a really quick question also on the shock. So I was wondering, the story I wanted to tell myself when we were thinking about the shock is something like, if a region experiences some kind of extreme temperature in 1 month or quarter, I think your data is monthly, isn't it? Yeah, 1 month, the expectation may be a little bit like a random walk. You kind of expect that to continue, or you pay a lot of attention to climate and weather-related events when you've just experienced one. Mm-hmm. And perhaps equally, if it's been a year since you experienced this type of events, you kind of really place a very low weight on that sort of possibility. And I was wondering if that's how. Is your VAR generating expectations in that kind of way, or are all of these events mainly kind of shock? So is there any predictability at all in the series, I suppose?
Well, I mean, there is some predictability in the sense that, I mean, I'll show it on this slide, but it would be true for our benchmark as well. There is some persistence in the ACI, right? Even if I just look at the ACI shock itself, but the half-life is also pretty small. So there is some persistence in these things, exactly because, some of these things carry over from 1 month to the next. So that it could be that that some of these effects are long lasting. I mean, the prime example is hurricanes or even a drought. Like a drought can take multiple months, and even if the actual effects of the drought have died down, the economic effects can still persist. So so it could very well be. Now, you mentioned regions. So one thing we didn't do here, partly because of the data availability of economic data, actually, is dig deeper into the regional analysis. This ACI index, which is really available on the web, you can Google it, is actually also available for different regions of the US. So at some point we actually tried to do something there. It just turns out there's not a lot of macro data at business cycle frequencies that is available at a regional level.
That's interesting. That's another thing I had in the back of my mind as well. It's like you might expect regions that typically experience kind of persistent shocks to be kind of more having adapted to that eventuality. So it may be less a big deal if you're commonly experiencing
I mean, that's kind of the prime example. Is not a US example, but the example I always tell about that is like the Netherlands, right? The Netherlands built these huge dams to protect themselves. Yeah, no, absolutely. So it would be very nice. We're still trying to find better regional data that we can actually use because we have the regional ACI data. We've done some preliminary work with employment, but here we really want to talk about actually like kind of a productive GDP or something like that, or IP. So yeah, no, thank you. That's a really good point.
Thank you.
If there are no more, sorry.
I think yes, you can continue now. Now we have no more questions for the time.
Okay, I just briefly want to mention, because Laurent asked about this at the beginning. I want to briefly mention robustness. Okay, so what I'm going to do is the first thing we're doing in robustness is we had seasonally adjusted everything. So let me show you the results without seasonal adjustment. They look very similar. Okay, the one thing, as I mentioned, the one thing that's kind of less robust is unemployment, but everything else goes through as before. Now, what about alternative transition variables? We can use, instead of just using this linear time trend, we can do a lag moving average of ACI. So that's what it looks like. Well, you know, okay, it certainly has kind of a more nonlinear shape. Let's see what the impulse responses look like. Well, very similar again, okay? So IP growth, same pattern as before. CPI inflation, same pattern as before. Interest rate, same pattern as before. Okay, unemployment rate, there's not much going on here. What about CO2? We can look at what has CO2 concentration been in the past in the atmosphere. Okay, so that kind of looks nonlinear as well. Okay, very smooth. And not surprisingly, we get very similar results. Okay, so here again, unemployment rate, as I said, that's the one variable where I'm not going to emphasize it too much. Here again, we get the same pattern as in the benchmark, but more importantly, we get the same result as in the benchmark for IP growth, and we get the same pattern for CPI inflation. Okay. Now, one thing you could ask is, hey, you have your ACI is constructed by basically looking at a benchmark period and everything relative to a benchmark. Why don't you just split your sample? Well, we can do that. Okay, how can we do that? We basically set C tilde equal to 0 until 1991 and equal to 1 after. Okay, and so here's what we find. We still see the same pattern for ACI, still see the same pattern for IP growth. In the point estimates, we see the same pattern for CPI. 0 is, at least for early horizons, included in the posterior bands, but still, given all the evidence that we have, given all the other specifications, that CPI inflation seems to go up at the end of the sample in response to an ACI shock, we think of that as a relatively robust finding. Okay, and I think I'm almost out of time, and it's good because I'm at the end. Let me just briefly highlight some takeaways. So we do find substantial changes in the effects of extreme weather events over the last decades, and we think that these effects are now big enough for macro people to care about them, especially if you think there is a chance that these extreme weather events are going to become even more extreme in the coming future. And why do we find the changes the way we do? Well, our working hypothesis is that there hasn't been enough adaptation, right? Apparently, Miami hasn't done a lot of what the Netherlands did, okay? And so that's it. That's all I have. So I'm happy to take any more questions if there are any.
Yes, I see that there is already a question. Ricardo has his hand up. I'm going to allow him to talk. Ricardo, I think you can unmute yourself now.
Yeah.
Ricardo is always on the line. There.
Hi. So question, whether you guys have tried with some kind of forward-looking variables. I was thinking something like stock prices, whereby maybe like, I don't know, 40 years ago, if there was like an extreme heat wave or something, people would think it would be a good opportunity to sell more, AC units or something. Whereas now probably the dominant effect would be like anticipation of some kind of government intervention, or, marginal increasing the likelihood of the government intervention or things like that.
Yeah, that's a fantastic point. Thanks, Ricardo, for that. what we did very early on in the project, we looked at stock prices, and we tried to look at house prices as well. But we didn't find anything very interesting there. Now, but so in the sense that the results with stock prices included in the VAR were very similar to what I showed you, and the results and the impulse response of stock prices themselves were not very interesting, so we took it out. But a priori, yeah, that's exactly the same thought that we had.
Thanks. So at the moment, I don't see any other questions, but I will go ahead and ask you another one myself then. And oh, I see that there's one up. Then I'll ask that one first because I've already taken the floor quite a bit. So Timothy Foreman is asking, or is writing this. So he says, it seems there are clear ways for adaptation to improve, for example, air conditioning and better predictability of weather events. Are there forces pushing in the other direction? For example, shifts in sectoral production?
Yeah, that's a really good point. So first, I mean, it's definitely true. So there have been some successes in improving weather forecasts, especially for hurricanes. I used to live on the east coast of the United States, and there in the Mid-Atlantic region, so I looked at these forecasts very closely. Now, in terms of sectoral decomposition, I don't have an answer to that yet. We did collect data on the different sectors. I don't know why my slides went back. But yeah, it's a really good question. I don't know the answer to that. We tried to look into that, but it was like at the end, in the end we narrowed it down, and we focused on the very basic macro questions, the very basic macro results. But that's something we have on our to-do list. We have the data for the different sectors, like not a very broad decomposition of different sectors for the US economy. And we want to look at that further. But right now, unfortunately, I don't have an answer to that. But that's a really good point.
So I see that David also has another question. So I'll get him the floor.
I've got a two-pronged question, if that's okay, Christian. So one,
absolutely.
So you just mentioned this. So you mentioned weather, improvements in weather forecasting. And I was kind of wondering whether that would be another approach at trying to kind of estimate these shocks, whether you could compare the kind of severity of the events in your ACI index with what was actually predicted by forecasters. That would be kind of a neat exercise, it seems.
Mm-hmm.
The other thing I was just intrigued by, this point that you also made a big deal of, that the actual size of the shocks hasn't increased, which is really quite striking.
Mm-hmm.
And I was just wondering, if you could say a little bit more about that. Is this shocks relative to what your model is predicting the size of the shock should be? Is that how we should understand this, or is this?
So it's the shock. It's the difference between. Think about it, our model has predictions what ACI should be, and we're confronting that with what ACI actually is. And that error term, the magnitude of that error term has not changed over time. Okay, so our model, it has adapted, obviously, because, at the beginning of the sample, the relationships were different than at the end of the sample. But our model says that the error that it makes is basically the same. Let me, maybe I can briefly just show you the data. I mean, this is just eyeballing it, but if you eyeball this right here, you see obviously after the benchmark period, the level goes up, but it doesn't seem that the volatility around these things has grown a lot. Okay, this is just an eyeball test, but that is exactly the pattern that our estimates pick up.
Yeah. I can't actually tell but yeah.
I mean, it's just an eyeball test. I mean, at least
it's an eyeball test.
If these were much more, so I couldn't tell either. But now knowing the result, it seems like the fluctuations have not become a lot more volatile. It's not like when you look at financial market returns and you really see, oh my God, there's really a period of extreme volatility. You don't see that here. That's the only thing I want to convey. Absolutely.
Fair enough.
Yeah.
And have you thought about using weather forecasts or that sort of thing as an
No,
alternative?
I haven't, but that's a great idea. That's a fantastic idea. We should definitely look into that. We'll have to figure out if there's an easy database, or if we could go back and scrape the web for these. I mean, because, well, I guess we couldn't really scrape the web because we go back until the 1960s. So, so I don't know. We'll have to figure out if there's a way to get those, but it's a really nice idea. Thank you.
Maybe somebody has done it already for you.
I know, that's what I'm hoping. With these things, that's what you're always hoping for, right?
Exactly. Google Trends for the meteorological web. Yeah. Very good. I think we're 1 minute over time, so I'm gonna keep the question for later, and I'm going to thank, first of all, you, Christian, for the really interesting talk, and very clear and very interesting, and all the participants to the seminar, and I look forward to seeing many of you in our next season of virtual seminars after the holidays. And with that, thank you very much, Christian, for the seminar, and goodbye, everybody.
Thank you.
Bye.
Bye.
Bye. Bye. Bye. Bye.